Swayam Prabha. Digital India. Educated India.
Today we are going to study torsion of non-circular shaft. You have already studied torsion of circular shaft, where you have seen when a circular shaft is subjected to twist, the shaft of uniform cross section will undergo deformation, and a typical cross section of the shaft will give rise to shear stresses, which are going to be distributed like this. The shear stress has a variation with radius, which varies from 0 to maximum value at the outer radius, and this shear stress is going to act parallel to the boundary, or in other words, at every point the shear stress is acting in the tangential direction. Now the question is, if the shaft cross section is not circular, it could be elliptical, it could be rectangular, it could be in the shape of an eye, in the shape of a T. So if such cross sections are subjected to twist, then how the stresses are going to be distributed over the whole cross section, that will be the object of our study. And we would like to start with, let us consider that we have shaft of uniform cross section all over the length. The section, as I said, it could be elliptical or rectangular. Now under the action of this torsion, the deformation of the shaft will take place, and this deformation will give rise to stresses at each and every cross section. Now if you look into a typical cross section of the shaft, let us consider that this is the typical cross section, and as we apply the angle of twist, as we apply the torsion, a typical point P on the cross section is going to move to a new position P dash, and this displacement is going to give rise some motion in the x direction, some motion in the y direction, and now the difference that arises between a circular cross section and the torsion of a non-circular cross section is this, that under the action of the angle of twist, any typical cross section will not remain plane. In the case of a circular section, the section will remain plane, but in the case of non-circular section, this will not remain plane. And if we assume that the shaft cross section is uniform all over, then in that case we can assume that the deformation of any cross section will remain the same along the length of the shaft. So we will consider that the section deformation, which is typically known as warping of the cross section, will indicate that this warping or the displacement of a point on the section in the z direction will be simply a function of its position. It is not going to depend on where it is located along the length of the shaft. So we would like to consider that the displacement in the z direction of any point on the section which is W, and this W is a function of x and y only, it does not depend on, so it is independent of z or the location of the section. Now, if we get back to the typical point P, which was located at an angular orientation of alpha with the x axis. Now, under the action of the torsion T, this radial position OP is going to rotate by some angle, and if we consider that the angle of twist per unit length is equal to theta, and this distance from the origin is equal to z, then the total angle of twist will be theta into z, and therefore, this rotation or the angle POP dash is theta into z. Now, we can calculate from this the displacements. So, if we now try to calculate the displacements of the point P, you can now see that this angle is alpha and this angle is theta into z. So, therefore, this angle is theta into z, and as the point P has shifted to P dash, there is a displacement in the x direction of magnitude PQ, and there is a displacement of magnitude QP dash in the y direction. So, therefore, now we can write that the displacement PQ, which is nothing but u, and this u, it is minus, it is nothing but PP dash. If this angle is alpha, we can take approximately this angle to be also alpha. So, therefore, it is nothing but PP dash sin alpha. And what is PP dash? PP dash is approximately equal to theta z into OP. So, this is nothing but theta z, and if we represent OP by R, so this is R, then in that case we have theta z R into sin alpha, wherein of course we have taken OP is equal to R. Now, if we write the coordinate of the point P, so P to have coordinates x and y, then we can write R sin alpha is nothing but y. So, we can have now u is equal to minus theta z into y, y is equal to R sin alpha. Similarly, by similar consideration, you can find out the distance QP dash. So, let us write now P dash Q, and that is the V displacement. So, that V displacement is PP dash into cosine alpha, and again we can write it is nothing but theta z into R cosine alpha, and since R cosine alpha is equal to x, so this becomes theta z into x, that is the displacement P dash q. And displacement of the point P in the z direction, which is W. So, W is nothing but we have W a function of x and y. So, therefore, we have now the displacement u, v and w of any typical point. Now, since we know the displacement, it is possible to calculate the strains, and then by using the Hooke's law we can calculate the stresses. So, let us now look into the calculation of strains first. So, if we now consider the strains epsilon x is delta u delta x, and since u is independent of x, so that becomes 0. Similarly, epsilon y, which is nothing but delta v delta y, v is independent of y, so therefore again delta v delta y is equal to 0, and epsilon z, the strain in the z direction, which is delta w delta z, this is a function which is independent of z, and therefore this is equal to 0. So, what we find is that this deformation is taking place in such a manner that the normal strains, 3 normal strains are 0. Now, let us consider the shear strains. Gamma xy is nothing but delta u delta y plus delta v delta x. Now, delta u delta y, if you see the expression here, it is minus theta into z, and delta v delta x is theta z. So, therefore, net is 0. So, therefore, there is no shear strain. Again, if we calculate gamma yz is nothing but delta v delta z plus delta w delta y. So, what we have, delta v delta z is nothing but theta x. So, therefore, we can write now this is delta w delta y plus theta x, that is the strain, shear strain, and it is non-zero. So, let us now calculate the other shear strain gamma xz. So, let us calculate gamma xz, that is going to be delta u delta z plus delta w delta x. Now, u is nothing but minus theta z y. So, therefore, delta u delta z will become minus theta y. So, this is minus theta y plus delta w delta x. So, if we write this, it is delta w delta x minus theta into y. So, please note that in this particular problem, out of the 6 components of strain, we have epsilon x 0, epsilon y 0, epsilon z also 0, and at the same time shear strain gamma xy is 0, and the 2 non-zero components of strains are gamma yz and gamma xz. Note that the cross section is lying in the plane xy. So, therefore, the cross sectional plane is xy and z is perpendicular to the section. Since we have got the strains, now we can calculate the stresses. Stresses would be, we will have then all the stresses going to be 0. So, we have sigma x 0, so also sigma y 0, so also sigma z, all these are 0, and since shear strain gamma xy is 0 here, therefore, we will have this tau xy, which is nothing but rigidity modulus multiplied by gamma xy, that is also equal to 0, and these stresses tau xz is equal to g into gamma xz. So, therefore, it should be g into delta w delta x minus theta y, that is the stress xz, and then tau yz is equal to g into gamma yz, and again when you substitute the value, so tau yz is equal to g gamma yz, and when you substitute the value it gives us g delta w delta y plus theta x. So, these are the only two non-zero components of stresses in a problem of torsion of non-circular section. Our objective is to determine these two non-zero components of stresses and their distribution. How do we go about it? If you consider that the stresses at a point in a body must satisfy the equilibrium equations, so therefore we must go back to the equilibrium equations. The equations are delta sigma x, delta x, delta tau yx, delta y, delta tau y zx by delta z equal to 0. Now, note that sigma x is 0, tau yx is 0, and tau zx, which is shown there, tau zx, it is not dependent on z. So, therefore, that derivative is also z. So, therefore, this equation is identically satisfied. Be whatever the value of the stresses, it is going to satisfy this equation. So, the first equation is going to be satisfied. Now, let us look into the second equation. Second equation is tau xy tau x delta sigma y delta y delta tau zy delta z equal to 0. Of course, we have assumed that there is no body force and therefore, the body force terms are absent here. Now, tau xy is 0. So, therefore, this is satisfied, this particular derivative does not exist, y does not sigma y does not exist, therefore, this is 0, and tau zy, if you see the expression for tau zy, we had tau yz independent of z. So, therefore, the derivative with respect to z is 0. So, therefore, this equation is again identically satisfied. Third equation is delta tau xz delta x plus delta tau yz delta y delta sigma z delta z is equal to 0. So, this equation sigma z is absent. So, therefore, we do not have this term, and the derivatives of the stresses tau xz with respect to x plus derivative of the stress tau yz with respect to y, sum of these two is equal to 0. So, therefore, now let us substitute the value of the stresses tau xz and tau yz and then see what this equation gives us. So, we will substitute the value. So, we will have delta x g delta w delta x minus theta y delta y g delta w delta y plus theta x is equal to 0. If we simplify, this gives us delta 2 w delta x square plus delta 2 w delta y square is equal to 0. You remember that this w is nothing but the warping function, deformation, distortion of the section. So, this is known as warping function, and the whole of torsion is dependent on this warping function. Stress tau xz depends on w, tau yz depends on w, and of course, the angle of twist will depend on the torque. So, the stresses are dependent on the warping function, and that warping function, if you look into the equation, it is a solution of Laplace equation. So, therefore, this warping function satisfies the Laplace equation. It is a solution of Laplace equation. Now, let us look into some other typicalities of the torsion problem and stress distribution. Let us consider thus one of the typical section. Let us say we have the typical section Now, we would like to concentrate on a zone here, and our z axis is oriented along the axis of the shaft. This is our x axis, this is y axis. On this section, we are going to have stresses, only non-zero stresses on this section, or if we draw it to a larger scale, let me draw it to a larger scale. So, this is my, this is x, this is y, and what I am trying to concentrate upon is a small portion here like this, and on this section which is perpendicular to positive z axis, we are going to get the stresses to be tau zx, which is same as tau xz. Similarly, stress in the y direction is going to be tau zy, and this section or this element, its outer normal is oriented in this direction. So, this is the outer normal on this section. So, therefore, this m bar outer normal to this element would have direction cosines, let us say L, M and N. Since this outer normal is perpendicular to both x and y, Therefore, we are going to have this direction cosine to be nothing but 0, 0 and unity. Now, the traction that is going to come up on this area, we can write now Sx. Sx is nothing but L into sigma x plus m into tau yx plus n into tau zx. Now, since stress sigma x is 0, tau yx is 0 and this n is equal to unity, therefore, this Sx is nothing but given by the stress tau zx. Similarly, Sy is nothing but L tau xy m into sigma y plus n into tau zy. Here again, since L is 0, m is 0 and n is 1, so therefore, this traction on this area is nothing but tau zy. Coming to the third component of traction Sz, that is tau xz plus m tau yz plus n sigma z. So, here L is 0, m is 0, n is 1, but sigma z is 0. So, therefore, the net force in the z direction on this plane is 0. Now, let us look into this relationship little more carefully. Now, if we just again get back to our area, that area we have concentrated upon, it is nothing but this. If we now consider the stress here is tau zx and stress here is tau zy, and let us say that the outer normal to this is the outer normal. You can approximate it by a straight line. This boundary you can approximate it by a straight line. So, therefore, this is the outer normal to the boundary, and let us say that this outer normal, this one has the direction cosine L, m and n is 0. Now, the stress, if I consider this area to be dA, this whole area to be dA, then we can write L dA into tau zx. So, the component of this force due to zx in this direction, that is going to give us the component in this direction. Similarly, if we try to now consider the component due to tau zy and its the force due to tau zy and its component along this direction and sum it up. So, it is going to be m into tau zy into dA, that is the component, which is now that is equal to, and then of course, we will have these two components only adding up together. So, that is equal to, if we say that the stress in this direction is given by tau zr, then that must be equal to dA into tau ZR. So, finally, tau ZR is equal to L tau ZX plus M tau ZY. So, this component is going to be like this. I want you to note this point very carefully, that this tau ZR is the stress acting in this direction, and it is really acting perpendicular to the boundary. So, this stress acting perpendicular to the boundary, this is given by this magnitude. And if you now consider an area, let us say that we will consider an area like this. So, this is x axis, this is y axis, and this is our z axis. Now, let us consider an area here, and this area, its outer normal, let us say that is equal to n, and this n would have direction cosine, let us say L m, and since this is in the plane of x and y, this outer normal is in a plane parallel to the plane x and y, its component, the direction cosine with the z axis will be 0. So, therefore, now you see, if we just calculate the traction on this area, since this area is free of any loading, we will find that we will have Sx, this is free of any external loading, and therefore, there is no traction in the x direction or y direction or z direction. Now, we will look into Sx component. So, therefore, it will give us L into sigma x plus m into sigma m into tau yx plus n into tau zx. So, therefore, this is now L sigma x is 0, this is 0, and this n is 0. So, therefore, this is 0, and we find sigma sy, the traction in the y direction, is L tau xy plus m sigma y plus n tau zy. Here again this is 0, this is 0. So, therefore, this is 0, and S z is equal to L into tau xz plus m into tau yz plus n into sigma z. So, here this Sz is again, we find that it is 0, and then this n is, since n is 0, sigma z is also 0. So, what we have is that this L tau xz plus m tau yz is equal to 0. So, since the surface is free of any loading, this Sz is 0, and if you try to now combine these two relations that we have derived, here this relation and this relation, they are indicating that Sz is 0, and this relation is indicating that tau Zr is 0. So, therefore, what it means is that this is equivalent to saying that tau Zr is equal to 0. So, therefore, this stress which is going to act perpendicular to the boundary is going to be 0. So, I would like to show you a sketch to illustrate this point. So, I would like you to look into this sketch. We are considering this element, it is oriented in the RZ plane. So, this is your R direction and this is your Z direction. The Zr stress is going to act on this plane. Similarly, the pair of this is going to be directed towards the center, and the complementary shear stresses which are going to come up on this face, it will be oriented like this, and on the other face it is going to be oriented like this. So, now this RZ stress is going to act on the outer surface, and this cannot happen, this is not there, in fact this is 0. So, if this is 0, this is 0. Similarly, the complementary shear stress tau Zr is 0. So, this is 0. So, therefore, since this curved surface of the shaft is free of any external loading, you have tau Rz 0, therefore, this tau Zr is also 0. So, that is the meaning here, that earlier we derived that Sz is 0 means tau Zr is 0. Let us look into how to get the solution for the warping function. This warping function was introduced by Sven, and later on a function was introduced by Prandtl, which is convenient for obtaining solutions to different geometries. So, we would like to consider this Prandtl stress function approach. Prandtl introduced one stress function, and he defined the stresses. We had two non-zero component of stresses tau xz, and he defined that this stress is given by delta phi delta y, where phi is the Prandtl stress function. Similarly, tau yz is given by delta phi delta x. So, phi is Prandtl stress function. Now, we can get some relationship between this Prandtl stress function and also the Sven warping function, and it is possible to also comment on the properties of the Prandtl stress function looking into the physics of the problem. We have already seen that tau xz was given by g delta w delta x minus theta y, and that is equal to delta phi delta y, and tau yz g delta w delta y delta y plus theta x is equal to minus delta 2 phi delta x square. Now, if we differentiate the first relation with respect to y and second relation with respect to x, I am sorry, this is delta phi delta x. So, if we differentiate this with respect to y and this with respect to x and subtract the second equation from the first, then we have delta 2 phi delta x square plus delta 2 phi delta y square is equal to g delta 2 phi delta x delta y minus theta then delta 2 w delta x delta y minus theta. So, delta 2 phi delta x square plus delta 2 phi delta y square is equal to minus 2 g theta. So, this is an important equation of torsion. So, therefore, the triangle stress function is such that it satisfies the Poisson type equation. Note that g is a material constant and theta is nothing but angle of twist per unit length. We will derive certain characteristics satisfied by or so demonstrated by this triangle stress function. We have already seen that if I consider a part of the boundary suppose we consider this is the outer normal to a part of the boundary, let us say this is n bar and this portion is lying in the xy plane and it has direction cosine L and M. If I say P Q are the 2 points that we are trying to talk about, let us say that P Q is equal to ds, and as we move from P to Q, we move in the x direction, that is going to be minus dx, and we move in the y direction, which is going to be dy. And now if I consider that this angle is equal to alpha, so this angle is alpha, therefore this angle is also alpha. We have already noticed that for a segment of the boundary like PQ, what we have is that L tau xz plus m tau yz equal to 0. The radial stress, the shear stress in the radial direction is 0, that stress cannot act perpendicular to the boundary. And now if I substitute the value delta, if we substitute the value for tau xz is nothing but delta phi delta y, and this is m, this is nothing but delta phi delta x equal to 0. If you look into value of L is nothing but, that is cos alpha, cosine alpha is nothing but minus dx by ds, pq is ds. So, therefore, we can write now instead of L we can write minus dx by ds. I am sorry, L is cosine alpha is nothing but dy by ds. So, therefore, this is dy, let us write again, L is dy by ds. So, we have delta phi delta y into dy ds, where ds is L, and then we have minus delta phi delta x, m is nothing but sin alpha is minus dx by ds. So, therefore, this is nothing but minus dx by ds. So, that is equal to 0. And now, if we see this, it is nothing but delta phi delta y dy ds plus delta phi delta x dx ds equal to 0, and this is nothing but, left hand side is nothing but derivative of phi with respect to s, that is equal to 0. What does it mean? That d phi ds is equal to 0, derivative of the phi along the boundary is 0, thereby it means that phi is constant along the boundary. So, therefore, phi is a constant, phi is constant along the boundary. And it is customary to take this boundary value of phi at 0. So, generally phi is assumed to be 0 along the boundary. We will also like to see there is another relationship which is satisfied by this Prandtl stress function phi. So, we have the typical section. If I concentrate on an element which is located at a distance x y from the origin. Now, on this section we are going to have stresses tau z y, and we are also going to get stresses tau z x, and let the area be is equal to dA. Now, if we try to calculate the moment of this moment of the forces arising out of the stresses at this point about the origin, dm is equal to tau zx into dA multiplied by the distance y. So, this is going to give us y tau zx into dA, that is the moment, and this moment is going to be clockwise. So, we write it negative. Then the moment due to tau zy into dA, that is going to be anti-clockwise, and the moment arm is x. So, therefore, we will have x tau zy into dA. So, this is the elemental moment. Herein it is going to be in the direction of the applied torque, which is considered to be positive in the anti-clockwise direction. So, the total moment we can get by integrating this, and therefore, that is equal to m, and that is equal to integration of minus y tau zx into dA plus x tau zy into dA. Now, if you substitute value for tau zx, which is nothing but delta phi delta y, and tau zy is delta phi minus delta phi delta x. So, therefore, you would have this integration y delta phi delta y dA plus x delta phi delta x dA, and if we consider that the area is A, so therefore, this integration is implied to be over the total area. We can write this thing as integration of delta phi delta y over the area. So, therefore, this is dx dy. So, also we have integration of this quantity x delta phi delta x dx dy. It is a product of two functions here, y and delta phi delta y. So, we can integrate this function with respect to y first. Similarly, here it is a product of x and delta phi delta x. Two functions are involved, and we would like to integrate with respect to dx. So, therefore, if we do it, we get, so integration of delta phi delta y with respect to y will give us y phi, and this integration is still to be done with respect to x. This is now going to be over the boundary S minus integration of this quantity is phi, differentiation of this quantity is 1, and now we have finished the integration with respect to y. So, therefore, we have to have this product again integrated with respect to y. So, therefore, we will have dx dy remaining here, and this is over the area A. By the same consideration, we can write this thing as S x phi dy minus 1 phi dx dy, and this is also over the area A. Since the function phi is 0 over the boundary, therefore, this product will always be 0. Similarly, this product is always going to be 0 over the boundary. So, therefore, their sum up over the whole boundary will be 0, and finally, we will be left with integration of phi over the area A, integration of phi over the area A. So, therefore, we will have now m as 2 times integration of the function dx dy over the area. So, the please note that I have made use of m. T is nothing but finally T equal to m, which is the external torque, and therefore this is 2 times a phi dx dy. Now, if we plot the phi function, let us assume that we have the cross section like this. Let us consider also that this is our x direction, this is y direction, and if we plot phi in the vertical direction, we are going to get, so we will plot this phi in this direction. For values of phi over the whole domain, we are going to get a surface, and that surface will look like this. So, the surface is really going to be a surface shown here, and this integral can be interpreted as, if we consider this cross section to be the base or xy plane and phi is in the vertical direction, therefore, this torque is nothing but equal to twice the volume bounded by the surface phi and the base, which is the xy plane. So, therefore, torque capacity is equal to 2 times the volume bounded by phi surface and section or xy plane. So, this is a very important information, that the torque capacity of this shaft is obtainable from the volume bounded by the phi surface and the section or the xy plane, when of course we are plotting this phi in the vertically upward direction.